Hello and welcome to Classes with Atish. In this episode, we'll talk about work, energy, and power. We'll go for conservation of energy, work-energy theorem, potential energy, and we'll solve a lot of problems around this. This is going to be an exciting chapter, so stay tuned. Okay, let us start with the definition of work. Work done is defined as the scalar product of force and displacement. Okay, so unit of work will be Newton meter. Okay, and so from this we can say if the force vector and let's say the displacement vector, they make an angle of theta between, then work done will be F S cos theta. Okay, so we can either look at this as the component of F in the direction of S, or we can look at this as the component of S in the direction of F, the product of that. Okay, so either way it might be useful in solving some problems. Okay, now we always say work done by a force on a body. This is very important. So work is always done by a force and it is done on a body. It doesn't make sense, for example, to say what's the work done when a body moves from position X to position X dashed. It doesn't make sense because you're not asking work done by what force, whether it's the work done by gravity, by friction, or the force that is pulling that body. So it always needs to be specified work done by what force and work done by which body. So the body which displaces from one point to another. If there is no displacement, again work done by all force on that body is zero. So let's do an example. Let's say there is an inclined plane. There is a body of mass m here. The friction coefficient between these two surfaces is mu. This angle is theta. Now question is find work done when body slides down the inclined plane. Okay, let's say this distance is given as L. Okay, so by gravity, by friction, and C by normal reaction. Okay, so how do we solve this? So let's draw the free body diagram of the mass m. So there is gravity in the downward direction. If this is the surface of the inclined plane, then there is normal reaction in this direction. Okay, and then there is the body sliding this way, so there is frictional force in the opposite direction, and the frictional force is equal to mu dot mu n. Okay, this angle is theta. Okay, so let's look at gravity. Now the total displacement, what is the total displacement? the total displacement is along the incline. So how much is that? Cos theta is L by, if this distance is d, so total displacement d is L by cos theta. Okay. Now, so first is, let's find out work done by gravity. Now gravity is in this direction, displacement is in this direction, right? So we have to find the component of gravity in the direction of displacement, component of force in the direction of displacement. So work done by gravity, let's denote by Wg, is equal to mg sine theta is the component of force due to gravity in the direction of displacement, and displacement is positive also in this direction, so both are positive, times d, which is L by cos theta. So mg sine theta times L by cos theta. So this is mgl tan theta. Okay. Now let us look at work done by friction. Okay. So now work done by friction. Now friction is in the opposite direction to displacement. So you have to be careful with the sign. So friction force Fr is in opposite direction to displacement, so we'll have to put a minus Fr dot times d. Okay, so Fr is mu times n and d is L by cos theta. Now how much is n? Because the body is in equilibrium perpendicular to the surface of the incline, n is equal to mg cos theta. So we can write minus mu mg cos theta times L by cos theta. Cos theta cancels out, so minus mu mgl. Okay. Now last one, let's find out work done by normal reaction. Now look at this. Normal reaction is always perpendicular to the displacement. Now Fs cos theta. So work done by normal reaction, because cos theta is 90, cos 90 is 0, so this will always be 0. So we can look at this. Work done by gravity is positive. Work done by friction is negative. And work done by normal reaction is 0. So work done can be positive, negative or 0 for different forces for the same displacement of the body. Okay. Okay. There is a semicircular ball. Okay. Like this. And the radius is given as r. Okay. Now there is a mass m at the bottom of this semi-spherical ball, and let's say a force is applied, okay, and and this is moved up to here. So at which position it makes an angle theta with the vertical. Okay. Find work done by F on the mass. All right. So if we see what is the displacement is this. This is the displacement vector. Okay. Now we know work done is force, dot product of force and displacement. Or we can say, let's say this angle is alpha. We can say Fs cos alpha. Okay. Another way to look at it is if I combine these two, F times S cos alpha. What is S cos alpha? S cos alpha is the component of S in the direction of the force. Okay. So maybe if I represent it with a different color. So S will have two components. Okay. So F times the component of S in the direction of the force. Now let me draw a perpendicular to this line from the final position of the body. Okay. And let's say this is O, this point is A, this point is B, and this point is C. Now S cos alpha, can we say this is AB? S cos alpha is nothing but AB. Okay. Now can we find AB? AB can be found out pretty simply. It is AB, so this is the radius R. So AB by R is sine theta. So this will be R sine theta. Okay. So the total work done is F R sine theta. Okay. So this is an example where we take the component of displacement in the direction of force. That way it's easier to calculate the work done. Sometimes you will do component of force in direction of displacement. Okay. All right. Next, let's look at another example. Let's say there is a massless pulley and it has two masses hanging on either side. Okay. This is M1, this is M2. Okay. Now M2, let's say it goes down by distance x. So what will happen? M1 will go up by the same distance x. Okay. Question is, find work done by gravity on M1 and M2. Also find work done by tension force on M1 and M2. Okay. Now M1's free body diagram, if I draw M1G, there is tension in the string. M2, if we draw M2G, there is tension in the string. Okay. So if M2 came down, basically there will be some acceleration in this direction and the same acceleration in the upward direction. Okay. So we can write T minus M1G equals M1A, and from this we can write M2G minus T equals M2A. Okay. Now let's solve for T. So if I have to basically eliminate A is equal to M2G minus T by M2. Okay. If I cross multiply, T M2 minus M1 M2G equals M1 M2G minus T M1, or T M1 plus M2 will be equal to 2 M1 M2G. Tension is equals to 2 M1 M2G divided by M1 plus M2. Okay. So we found out the tension, we know the gravity forces. So work done by gravity on M1 is, so M1G force is downward, however the displacement is happening upward. So if I consider the downward as negative, so I have to say M minus M1G times upward displacement is positive, so this, so minus M1Gx. Okay. Now similarly, work done by gravity on M2, so M2G is downward, so minus M2G times X is also downward, so minus X. So this is M2Gx. Okay. Now let's say work done by tension on 1. Now tension force is upward and displacement is also upward, right? So Tx, and this will be nothing but 2 M1 M2 Gx divided by M1 plus M2. Similarly, work done by tension on M2. Now tension is upward but displacement is downward, so minus Tx. So it is exactly minus of this. Okay. Now note here, the total work done by tension on the system is 0, is cancelled out. But the total work done by gravity on the system is not 0. Okay. So let's say there is a force given, F is 2I plus 3J plus 5K cap. So 2I cap plus 3J cap plus 5K cap. And due to this force, a body moves from its initial location of 0, 2, 3 to 3, 2, 0. Okay, it changes its coordinate. Find work done by F on the body. Okay. So based on definition of work done, we'll write it's the dot product of F dot displacement. Now we have the force 2I cap plus 3J cap plus 5K cap. So we have that vector. But what about the displacement? So displacement would be, so R initial is this. So 0I cap plus 2J cap plus 3K cap. R final is 3I cap plus 2J cap plus 0K cap. So the displacement vector is RF minus RI. These are all vectors, right? So RF minus RI, so 3 minus 0, 3I cap, 2 minus 2 plus 0J cap, plus 0 minus 3 is minus 3K cap. So we can substitute that here, 3I cap minus 3K cap. Now dot product is simple, so you multiply the I caps, J caps and K caps. So 2 times 3 is 6, 3 times 0 is 0, and 5 times minus 3 is 15. So this is minus 11 Newton meter. Okay, or the unit you can also write minus 11 joules. One more concept I want to talk about. Now, since work done is Fs cos theta, when cos theta is positive, work done is positive. When cos theta is negative, work done is negative. Okay. When work done is positive, when work done is positive, we impart kinetic energy to the body. So we add kinetic energy. And then when work done is negative, we take away kinetic energy. Alright, now let's talk about what is the situation if the force is a variable force. So long we were saying work is Fs cos theta. This is applicable only when the force is a constant force. But what if the force is a variable force? So for example, let's say here's the displacement in the x-axis and force in the y-axis. Okay, let's say force varies with displacement, some curve. Okay, now we cannot use this formula because the direction of force, the magnitude of force might be different. Okay, so what we do is we use calculus. Let's say at some displacement s, the force is Fs or the force is F. Okay, for some small displacement ds, okay, for some small displacement ds, the force will still be F. So we take this small displacement, okay, and the small work done dW will be equals to force times the small displacement. Okay, so whatever the value of force is at displacement S. Okay, now to calculate the total work done for, let's say, from S1 to S2, what do we have to do? We have to integrate f dot ds from S1 to S2. So which means we take small increments, of displacement from S1 to S2 and we add. So what we do that when we integrate, it is the area, the complete area under the curve between S1 and S2. Okay. So for example, let's say we are given force varies with displacement as a s square plus s plus 1. Okay. So then total work done, let's say we have to find work done by the force on a body when body displaces from s equals 1 to s equals 3. Okay, so what do we do here? We integrate f ds s equal 1 to 3. Now this is simple. A s square plus s plus 1 ds from 1 to 3. So this becomes a s cube by 3 plus s square by 2 plus s, and we take the limits from 1 to 3. So we can write a by 3 cube plus 3 square by 2 plus 3 minus a 1 cube by 3 minus 1 square by 2 minus 1. And then you can do the math. So 9a plus 9 by 2 plus 3 minus 1 is 2. Sorry, 3 minus 1 minus half is half minus a by 3. Okay, so you get the idea. So this is what you just solve this and you will get the answer. So 9a minus a by 3 plus 5. Okay. Now let's talk about work-energy theorem. Now before that, what is energy? Physicists define energy as the capacity to do work. So there is some correlation between work and energy. So let's find what that correlation is. So that correlation is defined by a theorem called Work-Energy Theorem. Okay. Now we define work as, let's say, integral force times displacement. Okay. Let's for a moment assume that there is displacement only in one direction, just to keep things simple. So dx, where the initial position was x1 and the final position was x2. So which means x2 minus x1 gives you the displacement. Now here obviously force is a variable force. So we can write force as mass times acceleration. Okay. And we can further write that as mass times acceleration is rate of change of velocity, dv dt. This v is of course in the x direction. Okay. So this we can further write it as x1 to x2 m. Now dv we can write dx times dx dt times dx. Okay. Now if I cancel out these and this, then we can rewrite this as, I will not write the limits yet, m times dvx, but what is dx dt? That is vx dvx. Now since the limit we changed, we can write it as velocity at position x1 v1 and velocity at position x2 v2. Okay. Now mass is a constant, but what is integral of vx dvx? It vx square by 2, and we put the limits from v1 to v2. Okay. And then this becomes m by 2 v2 square minus v1 square, which is, we can rewrite this as half m v2 square minus half m v1 square. Now what is half m v2 square? This is kinetic energy final minus this is initial kinetic energy, or the change basically is delta Ke. So what the work energy theorem says, the work done by all forces that are acting on the object is equal to the change in kinetic energy. I made a very important statement. This force is not just one force that is acting on the object. It is sum of all forces. What comprises of all forces? It can be all internal forces, all external forces, we also include, if we are dealing with a non-inertial frame of reference, we also include pseudo forces. Okay, so the work energy theorem says work done by all forces is equal to the change in kinetic energy. This is a very important concept. So in fact, let me write it down. Work done by all forces is equal to the change in kinetic energy. Okay. So if a body is acted upon by forces and the speed of the body does not change, then the net work done by all the forces is zero because there is no change in kinetic energy. Okay, so that is what the work energy theorem says. Now let's try to solve some problems. A body of mass 5 kg is acted upon by forces such that its velocity time graph is, let's say time velocity is this, and this. Okay, this is 10 seconds, this is 20 seconds, and this is 25 seconds. Okay, and this is, let's say, 10 meter per second, and this is 20 meter per second. Okay, find work done by all forces that are acting upon the body from time A 0 to 10 seconds, B 10 to 20 seconds, and C 0 to 25 seconds. Okay, how can we do that? So we can say work done by all forces is equal to the change in kinetic energy. So what is the change in kinetic energy between 0 to 10 seconds? At 10 seconds it was 10 meter per second square, so half m v 10 seconds square, and at 0 it was half m v 0 square. So this is half, m is 5, 10 square minus 20 square. Okay, so 5 by 2, 100 minus 400 is minus 300. So this is 150 and minus 450 joules. So it's 750. So minus 750 joules. So if the work done is negative, it means we're taking away kinetic energy from the body. So that is the reason the velocity dropped from 20 to 10 meter per second. Now from 10 to 20 seconds, we see there is no change in velocity. It is same as 10 meter per second. So there is no change in kinetic energy, so this must be 0. And again, from 0 to 25, so at 0 it was 20 meter per second, at 25 it is 0. So the change in kinetic energy is half m v at 25 square minus v0 square equals to half 5, at 25 it is 0 minus 200 square, sorry 20 minus 20 square is half 5 minus 400 1000 joules. A body of mass 1 kg is acted upon by some forces such that its displacement is given by 2t square minus t plus 1. Find work done by all forces from t equals 0 to 2 seconds. Okay. If you want, you can pause the video and try it out by yourself. But here is how we can approach this problem. So we know again, work-energy theorem says work done by all forces is equal to the change in kinetic energy. So from displacement we can't find kinetic energy, right? Here can we apply this? Work done by all forces is resultant of all forces times displacement. It could be a little involved process here, because then we will have to find mass times acceleration ds, and acceleration can be found if we differentiate this a couple of times, right? So velocity is ds dt and acceleration is d square s dt square. So if we differentiate s with respect to time couple of times, we will get acceleration. So this one will be 4t minus 1, and acceleration, if we differentiate this another time with t, it will be 4. Here it looks like the acceleration is constant, so the resultant of all forces is also constant. So basically the work done we can write as ma s ranging from s1 to s2. Now s1 we can find is the displacement at time t. Just substitute 0 here, so s1 is 1. And what is s2? s2 is the displacement at time 2, so 2 times 2 square minus 2 plus 1, so 8 minus 2 plus 1, 7. This is meter. So then we can write work done is mass is given as 1 kg, acceleration is 4 meter per second square, and displacement is s2 minus s1. Let me write down s2 minus s1. So 4, s2 is 7 minus s1 is 1, 24 joules is the answer. Okay. This can also be done using the work-energy theorem. How can we do it? We need to find the change in kinetic energy. So the change in kinetic energy is half m v at 2 seconds square minus half m velocity at time 0. Now velocity we found is 4t minus 1. How did we find velocity? We do differentiate displacement with respect to time one time. So ds dt is velocity. So we know 4t minus 1. So v2 is, if we substitute 2 here, so 4 into 2 minus 1, 8 minus 1 is 7 meter per second, and V0 is 4 into 0 minus 1 is minus 1 meter per second. So the change in kinetic energy is half m, we can take out as constant, V2 square, so 7 square minus V0 square, so minus 1 square. Or we can write half, 7 7s are 49, minus 1 is half of 48 is 24 joule. So in this case you can solve with both these processes. Okay. Say the displacement is related to time as this, t equals root x plus 3, and this displacement happens because of some forces acting on the body. Find work done by the forces from t equals 0 to 6 seconds. Okay, so we have this. We can rearrange this as root x equals t minus 3, or if we square both sides, x equals t minus 3 square, or t square minus 6t plus 9. Velocity is dx dt is 2t minus 6. Velocity at time 0 is minus 6 meter per second if I replace t equals 0, and velocity at time 6 is 2 into 6 minus 6, which is 6 meter per second. Okay. Now work done by all forces is change in kinetic energy. Now change in kinetic energy is half m v final square minus v initial square. Now this is equal to final velocity is 6 square, but initial velocity is minus 6 square. So this comes out to be 0. So see, although velocity changed, the magnitude of the velocity was same, which means we can say the speed remained same. So it can so happen that in the journey from, let's say, A to B, a particle's velocity, maybe it initially had a positive velocity and it went down and it had the same final velocity speed but in the negative. So let's say this was positive v and this was negative v. So some forces acted on the body so that its velocity time graph was like this. Okay. So although the velocity changed, the speed did not change. Speed remained v between these two intervals. Then the work done between these two intervals by all the forces is 0. Okay. Okay. Let's say we have a ball hanging from a string. And then there is a variable force F that is acting on the body, and it displaces the body very gradually to a final position like this, where this is theta. The length of the string is given as L. The mass of the body is m. So a variable force displaces the body, the mass m, very gradually from this position to this position, from let's say A to B, from A to B. Find the work done by F. You have to read it very carefully. It says a variable force displaces the mass m very gradually. Whenever you hear or see things like this, very gradually, it means it did not impart any velocity to the body. It was done very slowly, so there was no velocity given to the body, which means the change in kinetic energy is zero between A and B. Okay? Now, can we just use work-energy theorem and say, well, work done by force F is zero because there is no change in kinetic energy? Absolutely not. Because what does the work-energy theorem say? It says work done by all forces. Is F the only force working on the body M? I don't think so. There are tension forces in the string. There is force due to gravity. So there are other forces also working on the body. So the work-energy theorem says work done by all forces is equal to the change in kinetic energy. Here in our case we have work done by gravity. So in fact I should write all here. Okay, work. So what are all the forces? Work done by gravity, work done by the tension force, and work done by the force F is equal to change in kinetic energy, which is zero. Okay. Now we can write work done by the force F, because it says it's a variable force and it does not define the force at all. So it's very difficult to do force times displacement to find the work done by the variable force. In fact, there is no way we can do it, but we can use the work-energy theorem to say work done by the force is then, if we take Wg and Wt at the other side, it's negative sum of work done by gravity and work done by tension force. Now, can we find out the work done by gravity and work done by tension force? Absolutely. So let's look at this. The displacement is AB and the force due to gravity is mg. So we can say Wg equal to the force mg, which is in the downward direction. So all we have to do is this displacement vector that we have, can we find the vertical component of this displacement vector, which will be, let's say this point is C, which will be AC, and obviously it is in the opposite direction. So AC can be easily found out. So let me do the math here. OA is OC plus CA. OA is given as L. OC, so this OB is also L. So cos theta is OC by OB. Cos theta is OC by OB. OC divided by OB, or OC is OB cos theta. What is OB? L cos theta. Okay, so OC is L cos theta, plus we need to find AC, So AC is L 1 minus cos theta. Okay. Now, force is in the downward direction. The vertical displacement is in the upward direction. So both are different directions. So we have to do a minus times L 1 minus cos theta. Okay. So if we found out WG, now what about work due to tension? Now see, the displacement is this side. The tension is always acting normal to the displacement. Even if it was here, the displacement actually it will be here. So it is always normal to the displacement. So if force is this way and displacement is this way, then cos 90 is 0, so work done due to tension is 0. So then work done by the variable force is minus of work done due to gravity. So answer is mgl 1 minus cos theta. Okay. This episode is getting a little longer than I expected, and I have a lot more to cover. So let's conclude this video as part 1, and we will continue part 2, where we will start with a very important concept of conservative and non-conservative forces and build on top of it to define potential energy. Okay, so with that, let's close this video for today.